Today I will talk about an example pseudo-random generator. It is an insecure generator, but I will talk about the probabilistic aspect of how do we test whether a given pseudo-random generator is cryptographically secure or not. I will give basic overview of pseudo-randomness and explain to you a little bit about the probabilistic aspect. Okay, let's get started with a simple pseudo-random number generator. Okay, so the basic idea is pretty neat. What we do is usually we define this notion of distinguisher. A distinguisher is the one that you can imagine like a program which takes some string, okay, and the program is going to return 1 or 0, okay. It has some logic, it will return either 1 or 0. Okay, so the question now is what is the probability that particular program will return 1 when we give a truly uniform random number as an input, as opposed to a pseudo random number generator based number as an input. So we wanted to be able to compare the probability under which the program D returns 1 when given as input the pseudo random number. Also the same program when given as an input a truly random number. So let's do this. Let me share the screen with you and show to you a simple pseudo-random generator, and I will show you a Python implementation so you could get a concrete idea of this notion. Okay, so what I'm going to talk about is called a pseudo-random number generator, which is quite insecure. You will see why in a minute. So let's assume I have a pseudo-random number generator like this. Generator takes a seed S. S is a random number, truly a random number. You can imagine like this. What G of S is going to do is he's trying to come up with another output, right? The output is yes, followed by, I drew a line, 2 lines to show it's an append, right? You're going to append something. You're going to compute the parity of S, okay? So parity bit is basically, if S has even number of ones, the parity is 0. Otherwise, we say parity is 1. That's how I define parity in this video, okay? So how many bits are there in the output of G of S? So let's assume S itself is an n-bit number, okay? S is a secret seed uniformly chosen from the state space, of course, binary zeros and ones, right? It's an n-bit number. So then you call this G of S. So G of S will preserve n-bit here and then one more bit. So we can write it like this: G of S maps. Think about this. Is this G of S a pseudo-random number or not? Is G of S a pseudo-random number generator or not? Okay. S itself is a secure random number. Okay. So assume it's a truly uniformly generated random number. The question now is, what about G of S? This part is random, right? I'm claiming that G of S is actually an insecure pseudo-random number generator. Okay. So I will explain to you why G of S is insecure. So for that, we need to create a distinguisher program which will be able to distinguish between the G of S, which is a number selected from n plus 1 bit by running the G of S function, right? As opposed to another number that is selected from 0, 1 power n plus 1. Okay, so there are 2 things we are going to do. We're going to design a distinguisher D. What we are going to argue is that our distinguisher is a program. You can imagine like a function or a subroutine, which takes a string W as an input. Okay, the question now is, what is W? Okay, from a caller's perspective, 2 ways we can imagine W being. W can be G of S. That's the output that you get out by applying your generator on a CDS, right? What is the size of W? W is n plus 1 bit, right? Because G of S takes n bit and returns an n plus 1 bit. That's one option for W. Okay, what about the other option for W? The second option is W is equal to a truly random number generated from this binary 0, 1 power n plus 1. That means all n plus 1 strings, right? Strings of length n plus 1. And we select one of that randomly, okay? Uniformly selected from this binary string of length n plus 1. Okay, so now you have 2 options. So we will call D of W with this option first and check, does it return 1? Okay. Is this coming back as 1 or not? We are checking that. Okay. And we also select the W from this and call here and check again, is it also returning 1 or 0? Okay. So in order for G of S to be considered a secure pseudorandom generator, the distinguisher should be able to not able to distinguish, right? Because here our W is coming from G of S, here W is coming from a uniform string of n+1 length. So more formally, we can write it like this. We say the probability, right? The probability is PR notation. Probability that D of G of S, right? That means we run G of S on the input S, and then we feed it to D. What is the probability that this is equal to 1, right? And then we subtract that probability from probability of calling D directly on a random number R. Okay. What is the random number R? R is basically, you can view this as R also. You can say this is R, for example. Okay, no problems, right? So we are measuring these two probabilities, and we compute the difference between these two probabilities. Okay. If the difference between these two probabilities is very small, very negligible, there's a negligible function now. It's say less than or equal to some epsilon of n, which is a very negligible number. Okay, n is the length of the size of your secret, right? The CDS. So if the probability of D of G of S returning 1, subtracting from probability of D of R, okay. D again, you can imagine as a subroutine. That's how I will be showing you in a Python implementation in a moment. So we are going to see, is this difference less than or equal to n for all possible programs that we write, okay. If there exists a program D in which this is false, that means that D is a smart D that was able to distinguish between a truly random number and the output of a G of S. G of S is a pseudo-random number generator, okay. So to prove something is wrong, we need to build one counterexample. So if we can construct a D that is able to distinguish between the output of G of S from a truly random number, then we know for sure that the given generator is a weak generator. So let's take this example and build a D. So what is the D in this case? So we can argue like this. We just let me now directly show to you the D in a Python code. Is more or less easier to follow than what I'm saying here. We basically will take a word W, right? We ignore the least significant bit, compute the parity of it, and we check whether the parity is equal to the remaining bits. Okay, and the parity is equal to the least significant bit that we have stored separately. If that is true, then we know that we can return 1. So that's basically how we will be defining the distinguisher now. Okay, so let's get started with the Python code now directly. So what you're going to see is a Python implementation of this idea of the distinguisher, right? I hope that will help to get a good understanding of the probability thinking here. Okay, so we don't have to go into the details of how the parity itself is computed. Basically, I use the freely available parity check code online, so you can use any of these. That's not a problem, and I will show to you later. That's not the main important thing. So here is the generator S, right? Generator S on the whiteboard I explained ignores the well, what was it doing? It takes the input string or a seed S, right, and appends to the seed the parity of this S. That's basically what I'm doing here. So I take my string, I do a left shift by 1 position. That means my least significant bit is 0, and now I can XOR it with parity. So I have parity appended to the string S. Okay, that's basically what I'm doing. I can show you what the output of G of S is quickly, right? Suppose I take a random 10-bit number and I compute G of S. Okay, so I'll print now for you both yes and GFS. So it's clear for you, hopefully. So I need to do reload. For some reason it's not. Okay. All right. Now I can print this. Oh, can I not hear it? Give me a minute. I'm doing online. So okay, let's do this, right? Let's generate a seed yes randomly and print the seed in binary. Okay. And then we call the GFS and also print the GFS of that string. So we don't have to look at the other parts for now. Let me comment these parts so we don't bog down into too many details one step. Okay, so all I'm doing is to show you the behavior of GFS. Okay, so which is better to be shown in binary than string. So what is the first line? The first line is the CDS randomly generated by Python library. And the next line is basically GFS. So as you can see, there are 1, 2, 3 bits turned on. Therefore, the parity is 1 and parity is appended at the end. Okay, that's exactly the same string, right? And the parity is appended at the end. So let's try it one more time, see what happens now. Now we have 1, 2, 3, 4, 5, 6, even number of 1. Therefore, parity is 0 and parity is appended at the end. That's exactly what GFS is supposed to do. That's what we are doing here. Okay, now let's delete this because we don't need to keep on seeing this. Let's try to go into the details of the distinguisher. Okay, how is the distinguisher programmed? So the distinguisher is doing extremely simple. It takes some word W and extract the least significant bit. Okay, this is the way to extract the least significant bit, and then computes the parity of the input W, right, other than the least significant bit. So get rid of the least significant bit by right shift by 1 position. So now it's checking whether the least significant bit of the input is same as the parity. If it is, it returns 1. So and now we can check the behavior of D of W for different values. Let's try for a truly random as well as for pseudo-random, right? That's what we're going to do. So it's the first is, let me be more precise. The first is the pseudo-random and the next is the truly random, okay? As you can see, my R is coming directly from Python secrets library, right? And I must also call out the detail here. I'm doing n bits plus 1. Remember on the whiteboard I said GFS maps n bit to n plus 1 bit. So if you're comparing the effectiveness of GFS, you should also randomly select an n plus 1 bit. So that's basically why I am doing it here. Okay, anyway, so we first generate the seed, call the random number generator, pseudo-random number generator, G, which gives us an n plus 1 bit. As you can see here, you append an extra bit. And now we are going to compute now we are going to analyze the behavior of our W using D of W. And then we do the same with a truly random number in the next step. So let's try this both. As you can see, when we feed a pseudo-random number, D of W is 1. That's the reason why we get 1 here. It turned out that for this run, the D of truly random is 0. Okay, so let's do one more time. Now both of them turned out to be 1, 1. That's perfectly possible. Now let's do one more time. Okay, we ran 3 times. Okay, that's interesting. Maybe I should do it in a loop so we can count how many times we get 1 from the truly random, how many times we get pseudo-random 1. Pseudo-random is always 1 because that's how we programmed our distinguisher, right? The distinguisher will always return 1 when our W is pseudo-random, because that's how our W in this case is constructed, right? W is made of GFS and GFS is exactly doing this. So a number of times we get this 1 is always the same, meaning if you run it 10 times, all of the 10 times you will get 1 if your W is coming from a pseudo-random number generator, GFS. However, it may still return 1 for a truly random number W, but there is no reason to believe that more than half of the time that will be the case, because remember, in the case of a truly random number, I'm dealing with n plus 1 bits, right? And half of the distribution will end with 0 and the other half end with 1. Therefore, half of the time the program will return 1, and the remaining half it will return 0. That means the probability of getting 1 when W is coming from a truly random number is 1/2, right? Because only half of the time we'll have parity bit set to be 1. Okay, that means the difference with the probability is 1 minus half, which is half, which is more than negligible from a cryptographic perspective. Therefore, we argue that the G of S is not a secure pseudo-random number generator. That's the reasoning. Okay, so let me do a loop and show to you how many times we get the truly random number. When we feed D with the truly random number, we get 1. Let's do a simple loop. Okay, and I'm not going to do a print statement, otherwise it will have a lot of output. So let's just try to call this 10 times and measure the behavior of D when we feed with a pseudo-random number and later with a truly random number, right? That's what we're doing. So what I need is a variable. Let me call it count uniform, right? Which is set to 0, and I will check whether if D of, remember, D is my distinguisher. I'm feeding it with a truly random number. That's basically what I'm doing with the secrets.random bits, which is generating a truly random number from Python. If this is 1, I say I have been, well, I just basically increment the uniform plus 1, right? That's what I'm going to do. And at the end, I wanted to be able to print how many times did I get 1 from the distinguisher. Okay, let's see what happens now. As you can see, we ran it 10 times. The experiment ran 10 times, and 5 times we got 1 from the distinguisher, which is interesting. That's exactly why I said half of the time we will get 1 and the other half we get 0 when we run it with a truly random number, right? This is basically the truly random number, right? Assuming the secrets.random bits is a truly random function of Python. And we do, we check whether the D of R returns, D of R is 1. If it is, then we increment the uniform count by 1. Let's do it more. Let's try with 100 times. It may take a little while, but that's fine. 47 times we get 1, which is interesting. It's roughly 50% anyways. So let's do it 200 times, okay, which is still 50% approximately. So that's really neat that our distinguisher is able to distinguish between a truly random number as opposed to a pseudo-random number, because whenever we feed a pseudo-random number, it always returns 1, right? Because this is how the pseudo-random number itself is programmed anyways, the G of S, and the attacker knows G. G is a universally defined function. It's open. So there's nothing confidential about G. Therefore, the attacker is able to come up with a D like this. So that's basically it. Now we can go back to the whiteboard and reason about the summary. So what did we do basically? We are given a generator G, which takes an n-bit number as an input and returns an n plus 1th bit. It returns n plus 1 bit as an output. The first n bits are exactly the same as given S, and the n plus 1th bit is a parity bit. Okay, so we were able to write a distinguisher that was able to distinguish 2 things. If we feed in the truly random number, which is basically the number R coming from a string of size n plus 1, it may return 1 in some cases, of course. But if you feed in a string from a pseudo-random number generator, it always returns 1. The distinguisher is always able to return 1, which means the first part of the probability that I wrote it here, let me write it more precisely here. PR, the probability of distinguishing the G of S, when we feed G of S to the distinguisher D, what is the probability that it returns 1? Probability returns 1 is 1. It always returns 1 in our case. We checked in the demo. But if we feed in the distinguisher with a truly random number R, okay, What is the probability that it was returning 1? It was only returning approximately half of the time, right? We ran it experimentally. So, which means the difference between these two probabilities, is half, which is 1 minus half is half, which is a lot. Half is not a negligible number. Therefore, this G of S is insecure. Okay, this is how we reason about security of pseudo-random number generator. Okay, we should be able to build a distinguisher D and tell that the D is able to distinguish between a truly random number as opposed to a pseudo-random number. Okay, and the logic of G of S is known. That's how the distinguisher is able to distinguish. Otherwise, he wouldn't be able to distinguish, right? Okay, it's open security model. Okay, that's all. Thank you very much for your attention.